All right, I'd like to welcome everyone back to the S3D seminar series. Thanks for coming out. I know it's the end of the semester and busy, but we're glad you're here, and I think we have a really interesting talk today. So our speaker today is Joannah Nanjekye. She is a postdoc who's just started working with me this fall. So she got her PhD earlier this year from the University of New Brunswick in Canada. She's now a presidential postdoctoral researcher here. She's collaborating with me on a couple of projects and also collaborating with some other faculty here in the university. She has a great deal of experience with Python and systems programming languages research. She's a current maintainer of the Python programming languages, and particular sub-interpreters and extension models. She is also has authored a book on Python 2 and 3 compatibility. One of the big, some of you may have remembered the big issues in moving from Python 2 to Python 3. So that's definitely a big deal. And has served as a director and vice chair of the Python Software Foundation. Before joining CMU, she worked in industry at two fintech companies, where she worked in banking system integrations in Africa. During her PhD at the University of New Brunswick and the IBM Center for Advanced Studies in Canada, she proposed some novel memory management techniques, some of which she'll talk about today in the talk, that resulted in several published papers, but also several patents. So this is something that people really care about in the real world. She's received awards from the New Brunswick Innovation Fund, the Google and the Rust Foundation. She comes to us with a lot of background, which we're now, finding really cool for several collaborations. Anyway, with that, she's going to be talking about memory management techniques for dynamic languages. Thank you.
Thank you, Dr. Aldrich. So today I'll be talking about mostly my previous work, but also a reader about my current and future work. So this work, my previous work was done in collaboration with IBM Canada in a lab we call IBM Center for Advanced Studies at the University of New Brunswick. It was direct collaboration with IBM Canada in Ottawa, but also I would like to give credit to the managers there and my advisor, Dr. Bremner, who supervised this work for about 5 years while I was at UNB. So dynamic languages, it's debatable, but they are popular, but they will continue to be popular for some good number of years. And they are popular because they allow for rapid prototyping. Some have said that they are easier to learn, and many other things. And so right now we are seeing that languages like Python enjoy a great deal of downloads on the main languages, but also their packages as well. Very many studies have been done. When Python was released around 1991, it was not as popular as it is right now, but as the years have gone, Python has become very popular. Other languages, dynamic languages like JavaScript, have also followed suit. And so this motivates some of our work, or should give us reason maybe to look at some of the problems in dynamic languages. So one is that because they are popular and people are gaining interest in them, there is need for us to diversify their use. Diversification meaning if we can increase the domains in which these languages can be used, it will be very many beneficial for their users. So currently, Python and of course JavaScript ranks high for many domains, but there are still areas where they don't rank as high. For example, game development and IoT. Python is there, but maybe we don't see maybe JavaScript ranking as high there. So it shows that maybe we need to work towards making it easier or appealing for these languages to be used in as many domains as possible. So as they get popular, as we know, by virtue of their design, they come with some challenges, and so they are not fast as we can. We'll never make Python to be as fast as C, obviously, but we can make some attempts towards it. These were some workloads done at IBM, and they compared Node.js, Python with several other languages, and they noticed that dynamic languages, of course, were slower for very many workloads. And this is due to some of the dynamic design features in them that I'll be talking about them. That I'll be talking about today, and maybe some optimizations for some of those dynamic related features. So today I'll talk about three main aspects. One is the garbage collection, which was the main theme of my PhD work, its relation to extension modules, and some problems that are involved with working with memory management extension modules and native code. But also looking forward, give an introspection about what I'm working on here, collaborative work with Dr. Aldrich and Kyle, who maybe many of you know here. So garbage collection is a 70-year-old field right now, and I think people have started asking us, why are you still researching garbage collection? Aren't you done with all the problems there? But as architectures evolve and many applications, different tasks come up, garbage collections problems in garbage collection still remain relevant. So garbage collection is basically about automating memory management and taking away maybe some of that responsibility from the programmer, because if we make it a manual task, then it can get error prone because programmers can forget to deallocate memory that's unused, or deallocate memory very early on when it's not the right time to deallocate it. So in managed runtimes, garbage collection is a very key aspect, and almost all dynamic languages at least automate this task that we call garbage collection. For a brief background, garbage collectors are usually categorized in many ways, mainly three ways we can classify at least garbage collectors. We can classify them in how we identify objects, or how we allocate objects, and many other ways. But at least in most literature, the most well-known categorization of GCs is mainly in how we identify garbage, or how we identify objects that should be deallocated or that are no longer in use. And so we mainly know reference counting and tracing. So reference counting is about assigning something we call a reference count. And if there are references to an object, the reference count should keep incrementing by 1 or something. So if an object's reference count drops to 0, then it's considered garbage and we deallocate. Tracing, on the other hand, involves several phases. So we visit the object graph and mark certain objects are either in use if they have references, or not in use if they don't have any references. And we have another sweep phase that then deletes or deallocates those objects that have been marked as not in use. So many dynamic languages support either of, but Python, that I'll be focusing on today, at least CPython supports reference counting, and alternate implementations have very varying implementations of at least tracing based GCs. So garbage collection, very useful, but it's not a very free feature that comes in these languages. First of all, in most implementations of GC, the garbage collection task is stopped a while. That means that it stops the application program, does its tasks before maybe the application program can continue doing its task. What that means is that depending on how long that pause is, it affects many programs. Very long pauses impact different programs differently, negatively, not even in a nice way. When you're running a very small program, you may not know the impact of those pauses, but as your tasks get complicated, then you start to notice the impact sometimes of those pauses. So looking at all these problems or challenges, we identified three main gaps or opportunities for research. The first gap we identified was through modularity. So garbage collection is very complex, and we are dealing with very low-level artifacts of a program per se, bits. That's what we designed for. If you've ever written a garbage collector, you're always debugging things like memory leaks and very difficult bugs that you can spend several days on. So there is the idea that maybe some of these difficult components could be abstracted away into what we call into a module or a library, so that language implementers could just call into some of those methods rather than writing them from scratch, because they are very difficult to anyway implement from scratch. So getting them correct is hard. So Steve Blackburn in his keynote said that complexity is can lead to very many problems that could include security, but also performance. So if you're writing a very complex thing, you could err in some ways. Either you could degrade your performance, or even maybe overlook some of the security aspects of it because of how complex you're designing. So he argues that maybe if we reduce the complexity, maybe you could have a clearer eye on some of these other aspects. The other opportunity we saw is a performance opportunity. So around 2020, Instagram and Fission, they both released blog posts where Instagram said we are stopping to use garbage collectors. They use Python, and they're like, we are stopping to use the garbage collector because they debugged and noticed that there was garbage collection in CPython was causing a lot of overhead for the Instagram app. And Fission blamed garbage collection too for Rails, some of their Rails applications being slow. So they disabled their GCs for some time, but they noticed that was not like disabling GC was not going to be a solution. GCs come with some benefits. So instead, like us, we're supposed to explore some optimizations at least to make sure we still have the benefits of automatic memory management, but also running at the lowest overhead. The third opportunity we found was the integration to native code. Many languages, not only dynamic languages, including Java, they provide something they call extension modules, and they'll provide a header file, a C header file that people can write. C programmers can call into some of these virtual machines. And so we get three problems here. We have two environments. We have a VM environment and a C environment that we call the native environment. And both of these play by different rules. One assumes complete automatic memory management, and the other assumes that programmers take care of their memory. But then remember, objects from the VM and the C side reference each other and so forth. So it's easy to automatically deallocate an object in the VM side while it's still in use on the C side. So because of the challenges here, language authors just push this problem to the programmer. They're like, okay, manage it. That's why in the CPython API, because CPython is based on reference counting, C programmers are forced to mimic increfs, like increment the reference counts and decref the reference counts, so that they track references across the boundary. As you can see, it's a very manual task, and it leads to so many errors. When there is interaction across the boundary, what most of the challenges are, we are struggling with the automatic memory management on this side and the lack thereof on the other side. But the problems on native code can be summarized into maybe three main ones. One is how do pointer stability, how do we track references across the boundary, but how do we also make sure we correctly or accurately manage the lifetime of objects and we don't deallocate them when before they are supposed to be deallocated. But also, how do we manage the disparate memory models across the boundary? So we made several contributions towards these research challenges or opportunities. One is that through modularity. In 2019, we started a project at IBM with IBM Canada. IBM has a GC component or GC library that they call OMR. And so we started to demonstrate its use in dynamic languages. And we started with Python, a Python implementation we call PyPy. When we did that work, we had some good insights, some of which included overhead that some of those libraries introduced. So we went on to do a more intense analysis of GC overhead in general for dynamic languages, and came up with some optimizations related to the JIT and collections, but also we came up with some new some tool or an experimental FFI that's more garbage collection friendly for Python. And this will be the basis for my work today. So towards modularity, Eclipse OMR was an attempt towards making garbage collection development more modular. So they wrote, IBM, now I think it's an open source project, wrote a GC library that they call Eclipse OMR, and it contains basically components that developers can call into when implementing garbage collectors. So they support many GC policies, mainly tracing. I think they maybe work right now to support some sort of reference counting, but it mostly supported very high performant garbage collection policies that runtimes could implement. Built around this, of course, very key software engineering principles. Of course, we have to keep the performance high, but key to this design was portability, because Ruby, they tried to make sure that there was not many language-specific details here in the library. So in view of OMR, there are about maybe 3 views of it. So OMR provides a C interface and another layer that they call glue code. So this glue code is in the library, but it has to be replicated by each runtime that needs to integrate the Eclipse OMR GC in a runtime. Then we have, of course, the runtime specific code that calls this glue code. So remember, the glue code is in the library, but it has to be replicated to include in now language specific aspects that are related to GC in the runtime. What could this be? Maybe the object structure. How do the objects look like? That's unique to every runtime. The Python object structure is different from the Java object structure, for example. So then on the VM side, you have to maintain a thread, a VM thread, and maintain a heap, an OMR heap that has to be managed by the Eclipse OMR component. Runtimes can also support a private heap that probably is managed by another GC that's probably not Eclipse OMR or whatsoever. So our first integration was in PyPy, which was a Python implementation. And PyPy is very interesting. It provides a toolchain that they call the RPython translation toolchain. So RPython is a language for implementing interpreters. So if you use this technology, you write the garbage collector once, or even the JIT. You just write it once and it can get interpreted. It can, languages that are written in RPython automatically do get a JIT and a GC in it. So we we took advantage of that tool chain to easily integrate the OMR GC in it. So the tool chain has a couple of phases. It starts with our Python function objects, which is almost closer to bytecode. So the R Python code is interpreted with any normal Python interpreter to generate these R Python function objects that then go through graphing and type inference, which is adding typing information to the operations in the control flow graph. Very important in that workflow, in that tool chain phases are the transformations. So transformations add different information to the control flow graphs, and one of the transformations could add GC functionality into the operations of the graph. What does that mean? Is that maybe replacing malloc calls to allocation from the garbage collector. So we also wrote our own transformation there to invoke allocation calls from OMR to replace all the malloc calls before the operations are converted into any backend that could be .NET, Java, or C. Now PyPy converts or compiles to C. So we use mostly the C backend. Our evaluation was done on PyPy, but you could use the same GC to do evaluation like on PyCage, which was also a Racket interpreter implemented with R Python. So the case for modularity is usually, are you reducing the effort for the use of the modularity? So we did some software engineering metrics that maybe most of you are familiar with. We did some raw metrics, calculating like lines of code, the cyclomatic complexity, and yeah, we could see maybe the effort is less, at least for in the raw metrics. Maintainability index, we use standard formulas for this. This is a debatable metric. I mean, it makes sense, at least in theory, but I don't think this is a metric you want to go by. But at least we also saw at least 50% the OMR code through modularity would improve. How it would make it easier to maintain a code base. Lack of cohesion of methods. Of course, the OMR related garbage collectors have to do worse. Cohesion of methods is about how interconnected your code is. So the existing R Python GCs, of course, they are interconnected to many other functions in the interpreter. But because our GCs were calling OMR, it's easy for calling OMR methods, it's easy for them to be less connected to the other parts of the interpreter. So it made sense that they were not doing well, at least in LCOM. So most importantly, we also did the performance comparisons and found that the OMR garbage collectors, or the modularity related, they could improve collection time. But for mutator time, we saw an overhead that could be as high as 35%. This was for two reasons. Most of this overhead was due to differences in algorithms, but also what we call integration costs, the cost of calling a library. And this was more prominent around allocation and how write barriers were working. What can we conclude from here? I say modularity can still give us some good performance, at least in the implementation of garbage collectors, but it can also come with an integration cost because the calling a library is not free. There are ways to optimize this overhead, and we explored some of those ways. I mean, inlining helps a lot, at least for the implementation that's not best. So libraries can also implement what they call a fast path, which is basically minimizing when you call the library, but it just tells you that modularity has some costs that you have to go around. But also there are some times where you just can still have high performance, right? Yeah, so we also did an apples to apples comparison. Python, a tool chain for implementing languages. It means that if you have two interpreters implemented the same way, they are using the same garbage collectors, you can write programs, the same programs, and compare. So we saw a lot of overhead for PyHP, which is a PHP interpreter written in Python. These results, I mean, it seems like an apples to apples comparison, but there are some design specific things in the implementation of these languages that could make these results not very conclusive. For example, PyHP loads a live programming environment before it executes its first bytecode. So that, in fact, impacts many ways, at least in the results you generate for these garbage collectors. I think my thesis has more experimentation on GC modularity. You can go look. So, well, after this work, of course, we got a lot of insight into garbage collection itself, but on GC modularity. So we went on to do more intense profiling of overheads for garbage collection. And we zeroed in on one very key insight into where GC overhead also impacts JIT tracing. So I won't talk about everything we found out. I'll just zero in on a technique that we call optimal JIT resizing that ended up being much more interesting. So just to backtrack, Python translation toolchain, it implements a JIT, and GCs in the toolchain that languages that are implemented in don't have to implement from scratch on their own. So languages would automatically get a JIT and a GC. They use what we call tracing JITs. There are two kinds. You can implement JITs in two ways. We have method-based JITs, but then we also have tracing JITs. And just like the names, method-based JITs optimize around methods, and tracing JITs optimize around hot loops. So let's see. Tracing JITs have both an interpreter and a compiler. So at first, the application code goes through interpretation and some sort of profiling to identify very hot loops or hot paths in the execution program. Then it invokes what we call tracing, which is going through the operations in the hot paths and creating a list of those operations, what we call a trace. So that's what tracing is about, going through the hot loops and creating a list or a collection of those operations. Then the traces go through compilation. They are compiled, but just before they are committed, they go through a garbage collection phase. So the compiled code is executed, and execution of the compiled code calls into certain other components. Like it can call into like AOT, ahead of time compilation aspects, but also it calls into some aspects of garbage collection there. So our analysis, we saw some trade-off between garbage collection and JIT tracing. And this trade-off is depending on how the runtime, at least PyPy, how PyPy was designed. We saw that there was a correlation with very long traces and how high and the cost of the GC. It means that very long traces meant that these were objects that the garbage collector would work on. That means more GC pressure, or if it correlates to maybe long pause times for major GC. What does this mean concretely? So when a program runs, when tracing is happening, we use the metric we call resident set size here. And as we increase the trace limit, it also corresponded to hikes in the resident set size. So that means that the longer that trace, it means that more work for the garbage collector to do, hence more overhead for GCs. But what is that the real trade-off here? So in the first year, we showed that in PyPy, they had coded a trace limit to about 6,000. So we did some experiments and noticed, actually, when the trace is that small for some applications, the JIT does not have enough time or enough opportunities to optimize the program. That means it was beneficial for some applications to have a higher trace limit above 6,000. So then we said, okay, let's make the trace size. Let's remove the 6,000 and say, okay, the trace size is the maximum a program can ever have. But then we identified another challenge. We gave the JIT enough room to optimize, but then at some point, there were hikes or spikes in major and minor collection that would again cancel out the benefits we were getting from tracing. So at the end of that, they would see overhead. But this overhead is not because the JIT was not wrong. It would also be that we're doing so much work here. Now note, this is very rampant in PyPy, depending on how you design. In some cases, some of these JIT objects are really not GC susceptible, but in PyPy, they are actually. So PyPy is meta tracing. Also, meta tracing means we do not just trace the application code. We are tracing the interpreter as it is interpreting the application code. So if these are GCable objects, it means the surface area is larger and the GC overhead is even more prominent in that case of design. That's why this trade-off ended up happening. So we say what the insight here was just hard coding a trace limit does not work. Making it the maximum does not work. So we have to come to what we call an effective trace size, a trace size that gives the JIT enough room to optimize the program, but does not lead to GC overhead that cancels out the benefits we got in the program. So we proposed what we call dynamic trace sizing, and we use some profiling to come up to what we call an effective trace size. So the profiling was actually online, and the overhead of profiling was minimal. We got much more benefit. So with dynamic trace sizing is we profile the trace and identify what we call S effective and S max. So S max is like the maximum trace size a program can run. So we profile this trace before we commit it for compilation. And so the trace continues at S whatever we think. So there are times where S max doesn't give you the high GC overhead, and this we do it by studying the phase behavior of a program. So in other words, S effective is the block in terms of the trace, corresponds to the block with the highest exit, and then S max is just the total maybe trace size. So we have to make a decision at either running at S effective or S max, depending on profiling information we got from the phase of the program. So we implemented dynamic trace sizing in PyPy, but we also, because we wanted to demonstrate that it could work for other dynamic languages, we also did evaluation on Pyket, which is a Racket implementation that is also written in our Python. The results were, we got a bit of improvement. PyPy, we got as high as 12% for what we call simple, but these are micro benchmarks. If you run this with other workloads that maybe are long running, I think in existing work, this workload called Ahead, dynamic trace sizing had the potential to increase or to improve the performance by about even as high as 20x from like hard coding the trace limit of 6,000 was not good, and if you use our DTS, you'd get even 20x performance improvements from that. So that's about optimal trace sizing. The other overhead we attempted to at least optimize was around collections in dynamic languages. mainly two aspects. One is about the heterogeneity of collections and resizing features. And I'll talk about each of these. So in Python or Ruby or many languages, a collection can have items of different types. A list, for example, can have integers and strings. So we represent these objects we use a general type like object to represent these objects. To a GC, that means those are heap objects to manage. So we have to find a way. That means boxing is very expensive in some of these languages. Now, heterogeneity in collections is not just a feature of dynamic languages. It's also a feature of static. There are some static languages that do that. Now, existing work at least has some optimizations where they say, okay, if the user, we know that the language supports heterogeneity, but if a user only is having lists or collections with the same type, what we call homogeneous collections, they have an optimization for it, but they would still box heterogeneous collections. So those optimizations, at least in PyPy, it's called storage strategies. So we built onto storage strategies to support cases that at least they don't support. So to give you a picture of the impact of heterogeneity, this is how often, at least in the standard Python benchmark suite, this is how often collections transition from being of the same type to of disparate types. So lists transition the most, at least from empty to some type. Now, empty is an overestimation. It could be empty to homogeneous, right? But at least you could look at other transitions. And yeah, we're seeing at least dictionaries as high as 41.7. Now we compared the problem with optimizations that just handle homogeneous collections is that when a list becomes heterogeneous later, just by one item and the list is already long, the optimization has to rebox the items. So that optimization is actually becomes bad or worse than not having it, right? So we build on top of that work of storage strategies and through a technique we call type-based stores. So type-based stores, instead of still boxing heterogeneous collections, we would disrupt the structure of the collection and split the object by type and apply the same homogeneous related optimizations there. So we would apply storage strategies after disrupting the structure of the collection. But now, since we disrupt the structure, how would we handle reads if a user says, I want my item from position index 1? We have already disrupted it. So we had to maintain a map, at least mapping things from the original structure to the alternate structure. Good for us in PyPy, this was not very like an extra map. They already supported maps for even with storage strategies. So this was not on an overhead. But as you see in some of our evaluation, this map we maintain to track can introduce overhead in both memory and performance in some ways. So this map, we are basically maintaining like, oh, this item before splitting into type-based stores, it was at 0. And so now it's in this store, integer store, and it's at index 1, so that we can use it for update or reading in the future. So we applied type-based stores to PyPy, and we saw mostly improvements, on average about 12%. It could get as high as 60%. The memory footprint, it was a mixed story. As you know, that map introduces like memory overhead. So it's easy to have good benefits and a very high benefit very high impact, at least memory-wise. For dictionaries, we never needed to support like a separate map for tracking because keys are unique, at least in PyPy. So there was no need to do that. So we also evaluated the impact we get. Remember, the map helps us track, but there is overhead in just reading it before servicing and a list operation or a collection operation. So we evaluated some of that overhead, but as you could see, we have like get in dictionaries being very slow because of the operations we do around the splitting, but also checking. But as I showed on the previous slide, when these operations are working in a mix in a more realistic workload, overall, the optimization would give better results. Of course, we had some workloads that. Now note, our optimization was for heterogeneity. So if we had workloads that depended on mostly homogeneous collections, of course, we would not see that same benefits because PyPy would work better there. The default branch of PyPy would work better. Yeah, so that's about type-based stores. Now I'll talk about the other problem we optimize, which is collection resizing. So if you're familiar with how we support resizing in dynamic languages, we give the user the impression that their collections are actually dynamic. But underneath, we create very static data structures, store the items, and when that internal structure is full, we just create a new one and copy the items. So it's very slow. In CPython, I think we create, if a user creates like a list of 3 items, we create an internal static one with 6 slots. So if you max out the 6 slots through expansion, we have to create a larger structure and then copy the items. And that's why supporting this feature is slow. So existing work proposed what we call presizing. So presizing is we try to predict like the user behavior of how a list is going to behave over program execution. And we say, okay, if we assign it 96 slots, then we will reduce how many times we have to create new stores, okay, new internal structures, and the copying cost will be less. The problem with existing work is it did not take care of some of the exceptions around the allocation context, but also how to manage the branches that are taken through. I think there are only 2 papers, okay, before our work, there were only 2 papers around the presizing, and they all did not take care of branches. Remember, if you do not take care of branching information, that means you could still give a small size. In the best case scenario, you just give it a larger size, but you will not have solved the problems that come with presizing. So we made an assumption around correctly identifying the context, the allocation context, and in effect the branches by basing on the stack height of a program. Now, presizing is based off profiling. So when we use the hypothesis around the stack height, we would at least uniquely identify the calling context most of the time, and would be able to precise or predict the sizes of collections in our profiling at a much more accurate rate. So I won't talk about this stack height profiling. Maybe you can read my thesis. But this stack height profiling is not very accurate sometimes. You can have duplicates. Duplicate stack heights mapping to the same call path or same call context. We applied some deduplication methods, something we call active record resizing, function cloning, and many other things. Our accuracy was above 85%, but that's also a threat to validity. We are able to at least 80% of the time uniquely identify a calling context, but there is a 15% chance that you still have some noise in the profiling. So what do we concretely mean by the allocation context? This is an example of a few lists. So R and K or list EX on line 5, it's impacted. There is first of all a flag. Around 7, it could either take that if or that else. And also, to make matters worse, that list could be changed in different calls of a function, right? So you have to track the sizes for that. So we did some profiling. For this work, profiling was offline. Again, our main contribution here was not really about how you store the profiles. It was about how can we correctly at least identify the allocation context to allow us correctly predict the size of a collection. So for us, the profiles of the context identifier were offline, but of course, to know how to allocate a given object, you have to have that information of the object somewhere too. So we stored that in an object header. We reuse the identity hash because of how Python works. They force an identity hash even for objects that don't need that field, right? So for things like lists, we could reuse the identity hash and overwrite and store our information there. But for things like dictionaries, remember the identity hash field there is used, and so you have to enlarge the object header to just have that information to correctly predict. We maintained also that map in the runtime because PyPy already has those maps, so it was not like extra overhead. So for lists and sets, the impact on the object header was not there, but for dictionaries, we enlarged the object header in some way. So for this evaluation, we had to get more workloads that could work. The biggest challenge with evaluating this was you have to get the workloads that were very collection intensive for you to see the benefits you would never have here. Again, the assumption here is that original profiling is offline, other than the updates we do to the header and the reads we do from the header. And we saw good performance, both memory and evaluation, but we noted that the performance improvements were much more apparent in workloads like Delta Blue that were very collection intensive, meaning that they used a large number of collections. So this was done in PyPy, but I have more evaluation that we did for Racket and Ruby, for Topaz and PyCat to also demonstrate that we could have. Now there we had to do something different. We had to make this presizing modular again and put it in Python that it could get reused. Now collections, a library like that is not like a JIT or a garbage collector, because the way collections are implemented in every language is different. So we use some meta programming aspects to be able to just achieve that modularity that could support Topaz and PyCat. We got some interesting insight also. This was not part of our analysis for the stack height. So we ran a few benchmarks, and our goal was to see, could we identify certain phases in program behavior based on the stack height? And indeed, we could see some phases where the stack height would start out being low and it would just hike at one point. Of course, certain programs, the phases was not very maybe apparent. Richards, we could see N-body, the phases in terms of the stack height as a program ran, where maybe Pico, the web. But this gave us insight that this assumption on the stack height could inform some other optimizations. And there is a relationship between the call site and certain aspects about garbage collection. One of the insights, other than that, just that programs exhibited a certain phase when you assessed its stack height, there was a relationship between the stack height and the life size. The life size means the number of objects that are alive. So this is the correlation we saw between the stack height and life size. What does this mean? So Google wrote a paper where they profiled the life size, and the profiling was very invasive. And we saw that if instead of doing that invasive profiling, the stack height could be a proxy for life size for all those GC optimizations that people do that are based off the life size. So this takes me to our last contribution, which was around native code. To just rephrase, the Python CAPI, Python exposes what we call Python.h, and it's an attempt at either calling Python in another environment or calling another environment inside Python. Shares the same problems, pointer stability and lifetime complexities. The Python CAPI has more problems. It assumes objects never move, and it ties these implementations inside the design of it. So the problems are really, well, how do we identify a root? Because that's the biggest problem for pointer stability, and maybe object lifetime management. So we implemented a new FFI we call CyStck, experimental FFI. There are other FFIs like HPI that are being implemented in the community, but we did not fully commit to the technologies under HPI, which is fully commit to handles. Instead, we used a hybrid of a stack and very lightweight handles that had much more less overhead than the full handles. Now, the stack and handles in CyStck, they perform to, well, of course, some of the similar purpose, like interoperability, moving objects between the C and Python. But for us, they do more than that. They help us to track references across the boundary and help us know when to correctly deallocate the objects. So we were able at least to know, at least to a high degree, how correctly identify pointers across the boundary. But one insight we found is that reachability alone was not enough to determine when to create an object, to deallocate an object. So we would correctly identify references through reachability, but that was not enough because some C functions stay longer than the function that created them or that uses them. So some of those objects we had to make them seem alive longer than the references they were involved in. We had to do again another technique to completely automate GC. We did something we call process introspection to further isolate some of those cases. For PyObjects, those completely get handled by reference counting, but for C objects, we had to attach some other notations or policies to them to correctly know when to do the allocation. So CyStck, because of process introspection, it had more overhead compared to that Python CAPI, but it was expected because we did more automation in terms of memory management. It was more GC friendly. So if we assumed at least it gave us a path to even correct garbage collection, but we could still improve aspects of it to still be performant. We were copying very less bytes across the boundary, which is also an indicator of better performance, at least in the future. Yeah, so that's about my previous work. And right now I'm still working on Python, but with a slightly different focus, not really about memory management, but on something we call distributed time-sensitive applications. Applications where deadlines are very key. For example, in this case, this is about an intersection, and we have a deadline of about 500 milliseconds. We have to ensure that placement of tasks in a cluster of devices at least works within that deadline as indicated. So my work here will be building on a project that's already existing that I think Kyle and Dr. Aldrich are working on, called TT Python. it's an attempt, it's like a domain-specific languages that helps programmers view a distributed, have a global view of a distributed application. So for my time here, my goal is to make it easier for to program correct distributed time-sensitive application for IoT devices, but also provide some demonstration that they can be used in the real world. Specific directions I'll be taking in the next years will be adaptive mapping. I'll be working on improvement of the placement of the tasks on the devices, but also helping developers with debugging tools that can give them introspection into maybe some specific bugs, but also things like how devices are working in terms of power usage and if they are within the right deadlines. So for adaptive mapping, we are building on some algorithm with our collaborators, one from the electrical engineering and somebody else from Arizona. And we are trying to make sure that the placement of algorithms to a device network works within at least our timing constraints, which we call MakeSpan, but also we are adding on to what we call the power usage. The idea that at least we should be able to trigger, if a task requires maybe less power, at least we can trigger a device or do some modification in the cluster environment to make sure we are running at the optimal power needed to service a particular device. So this would be an example of the network and the mappings to it that's informed with at least efficient information on MakeSpan and power. So debugging is just a set of tools to give insight into maybe the power, but also the design constraints at hand. And we also have collaborations for case studies to just demonstrate that Python is useful in the field for actual developers. Okay, with that, I would love to end my presentation because I think time is almost up, and I'll take some questions if we still have any time for that.
Yeah, so we do have time for some questions if anyone has something they'd like to ask.
So how does this OMR reusable collector compare to MMTK?
Yeah, so that's an interesting question. So OMR achieves the same design problems like MMTK. I have also had a collaboration with Dr. Blackburn. We also did some work on MMTK in our Python. The design is a little bit different, but they err on different sides. So MMTK does a lot of hide, like encapsulates so many details from the programmer. It's a lot of encapsulation. It hides, which is good. I mean, you don't want to know too much. And OMR is on the other side. It exposes a little much more details. How is this a good thing and a bad thing? It means that the OMR garbage collectors, you can easily introspect them, do some analysis on them and know where the bottlenecks are. While here, because of encapsulation, you can just do much, not much with them. If you have an issue, maybe it has to be fixed in the library. There's a lot of analysis for GCs that's important that you had the full view of the implementation, or you had too much control about how a GC is implemented. So the differences in the design decisions they took, they each have their own benefits. There are times I feel that OMR could have been much more encapsulated because that's the whole point of portability, right? Just give enough for the developer for a given runtime, right? But you can also do too much of it. And I think, so that's the biggest difference, at least I saw, because the OMR, most of the development is in-house at IBM, okay, at least the GC work. It's not done very outside. So it's not benefited a lot from innovations on very new cutting-edge GC policies. While MMTK is open source, it's been researched, and then so Dr. Blackburn and his team have like 20 years of very high intensive innovation. So they'll have very cutting edge things like IncreMinimac, InMix, a very good GC policy that maybe IBM has not gotten because they just closed off their source for. That's what I would say. The policies in MMTK are a bit cutting edge, and that helps with some of the overhead I showed here. It could be elevated by robust garbage collection policies.
Could you explain more about the differences between the handle in HPy and the lightweight handle in the CyStck?
Yeah. So it's the handle in CyStck. It's just a small indirection to the object itself, right? While the handle in the handles in HPy, it's very evasive. There are some modifications in the object header to just even resolve what you're pointing to, right? So processing where the object is in HPy requires a little bit more work. For us, it's a very simple indirection to it, so we don't require too much processing to know where the object is. Yeah, so I think it's much more easier if you saw the implementation to know the actual, but the differences is in how we eventually process the actual Pi object. They are both in directions. One requires much more work to end up resolving the actual Pi object, while for us we do very little work. But remember, we also have a stack, which is also more work for resolving things around Pi objects and C objects. But the stack gives us much more accuracy. It's a trade-off we made in terms of knowing the object lifetimes and accurately know the pointers between the interfaces. HPy still uses increfs, just like the Python C API. So I would say we gain some benefits from the lightweight handles, but some of that we get it back from the stack side. It's just that we have more benefits for that additional functionality too.
So I have a question. As someone working on language implementations, and in particular memory system implementations, I wonder if you have insights or feedback that language designers should consider in order to help make your job easier or help make make it simpler to provide these nice high performance extensible memory management systems.
Yeah, so I think insight mostly is for the language implementers, right? You want to have a more opaque, an API, for example, in the context of memory management. First of all, there are two aspects you need to make sure at least adhere to in your design. So make sure that the memory model you expose on the API itself is not very detailed, so that it can be easily implemented by at least alternate implementation. That's usually the challenge, the memory model, right? If it's not as opaque as it should be, like for Python, PyPy is just struggling for compatibility just because of the memory model. Two, you do not want to commit to a particular GC policy in your APIs. This was a problem made 30 years ago, and now it's very bad. It's becoming impossible to solve because of incompatibility, right? CPython, even Ruby, they committed to putting reference counting semantics in the Python API with incref. Now they want to move to a more tracing GC, and they don't know what to do with the increfs and decrefs. I think there are ways to abstract away implementation details, at least in the API itself. I think opaqueness, and avoid borrowed references, maybe. borrowed references bring out a lot of bugs that are just very hard to solve in that interaction. They complicate resolving object lifetimes, even just identifying pointers, because borrowed references is not a real, it's not we just borrow a reference, and it's hard to correctly know when it's no longer in use or it's in use. So I don't know. They have their own advantages. If you can't do it right, maybe, I don't know. Yeah, they're just difficult to handle. Yeah.
Any other questions? If not, thank you again. Nice job. Thank you for presenting.